Okay, so the Fibonacci sequence is essentially a sequence or series of numbers that starts with 0, 1, 1, 2, 3, 5, 8, and so on. Starting from 0, every number in the sequence is a sum of the two numbers preceding. So in the sequence, the 2 comes from 1 plus 1, the 8 comes from 3 plus 5, and etc. The formula in more mathematical terms is S0 equals 0 and S1 equals 1. The numbers following the S1 term can be summarized with Sn equals Sn minus 1 plus Sn minus 2, as you can see on the screen. This sequence concept was introduced to Western European mathematics by an Italian mathematician, Leonardo Pisa, also known as Fibonacci, in 1202 in his book, Liber Albaci. He used a sequence to mathematically show the number of pairs of rabbits that can be reproduced from a single pair of rabbits in a year. Hence why the S1 term is 1. When the sequence is visualized on a grid with each number representing the length of a square, a spiral can actually be seen. So Sri will actually go more in depth on this, but this spiral can also be found in nature. It can be seen in the array of seeds in a sunflower and the spirals in leaves, branches, petals, and even broccoli.
Okay, so Daniel just introduced us to the Fibonacci series. And one of the very common things that we're going to see with the Fibonacci series anywhere in mathematics is this relationship with something called the golden ratio. And that's what I'm kind of going to describe right now. So we have our Fibonacci series. And we just talked about earlier, it starts with 0, 1, and we add the two previous terms to the next term. So 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, and so on. That's enough for now. And this goes on forever, as we kind of talked about. Now, the golden ratio is commonly denoted in mathematical notation with the Greek letter for phi, which is kind of like a 0 with a line through it. Now, phi is equal to roughly, since it's an irrational number, it's equal to around 1.61803, and there's a bunch more. It goes on forever. It's irrational. One of the other ways you can write phi is this way. So we have phi is equal to 1 plus the square root of 5 over 2. So these two are the same thing, basically. Now, how do we link these? How are these two linked? So the way that I best think of it is kind of doing this thing called Fibonacci term division. So what does this mean? So we have Fibonacci terms, and we're doing something with dividing them. And what this means really is we're taking two adjacent terms in the Fibonacci series, and we're dividing the larger one by the smaller one. So for example, let's take these two terms, 3 and 5. So we take the larger number, 5, and we divide it by 3. Now this gets us 1.666, and this goes on forever. Okay? See, this is kind of close. You can work with this approximation. Now, the higher the number the term is in the Fibonacci series, the better the approximation for phi is. So let's take 13 and 21. So we take 21 divided by 13, and this equals 1.615 ... a bunch more numbers. See, this number is already a much better approximation than this number. Okay, so basically, what it means is the farther along the Fibonacci series we choose our pair of adjacent numbers, the better approximation we are going to get for phi, the golden ratio. So what that means is, if you can write a little formula for it, we have an, which is the larger term in our pair. We divide it by an minus 1, the term directly before it. We will get approximately phi. Now, we're going to talk about some of the places where these two things appear in the natural world, such as in architecture, design, and engineering. So Christopher and John are going to take you right there.
So now that we know the connection between the golden ratio and the Fibonacci sequence, let's jump into Minecraft to see how they applied it in architecture. There's this old idea that the golden ratio is the most beautiful ratio between two things. This line of thought came from these two Greek ideas: the desire for beauty in architecture, similar to Roger Scruton's ideas that we covered in TOK, and the belief that beauty can be quantified in mathematics. Pythagoras believed that the most beautiful and pleasing proportion is created when a line is divided so that the ratio between the larger and smaller of the two parts is identical between the original line and the larger of its subdivisions. Basically meaning use the golden ratio to make beautiful buildings. But because the golden ratio is an irrational constant, Greek builders used the Fibonacci numbers to approximate the golden ratio. So if I'm building the foundation for a building and use 21, 13, and 8 as my psi links, I'll be integrating the golden ratio into my building. So I just built the foundation on the left, and here we have a building I made with the golden ratio as the sides. So if we wanted to make a building that has all of the digits of the Fibonacci sequence in it, then that's what we got here. And I think that means my building is objectively beautiful, according to Pythagoras and a bunch of other Greek architects and Greek intellectual thoughts. Some other buildings that include the golden ratio are the Pantheon, the Taj Mahal, and the Great Pyramid of Giza. So, as you can see, my building is obviously very similar and identical. It also appears in other arts, for example, the Mona Lisa and in the School of Athens.
Now, we'll cover some practical applications of the Fibonacci sequence. Specifically, we'll look at one example from computer science, which is known as the Fibonacci heap. Now, what this is that it's a tree data structure comprised of nodes which contain a value. So let's say 23 is a value, and the nodes beneath it are always greater than it. So let's say this is 49, and then this is 51. And this has a degree of 0, because it's in the first row. This has a degree of 1, and then this has a degree of 2. Now, if we want to add another tree to this existing tree, let's say it's over here, it's 6, 17, and then 9. If we want to add these three values to this, it's simply merged, like these point to each other, and then a new minimum value is found. And an interesting property of this is that the corresponding degree of each node, 2 greater than that, or the corresponding Fibonacci number to 2 greater than that, is always less or equal to the size of the node. Now, as I write out the Fibonacci sequence, I'll explain to you what that means. So let's say we have 23, which has a degree of 2, because its smallest child has a degree of 2. It really has 3 rows, and the first row is 0. Now, to take the value 2 greater than 2 is 4, so we look at the fourth Fibonacci number, which is 3, and then the size of this, of all the values under the node, 23, which is 5, you can see there are 5 numbers, is at least 3, is at least corresponding to 2 greater than the greatest degree, like that Fibonacci number. So the Fibonacci number here for 4, the fourth Fibonacci number is 3. Here we can see 5 is greater than 3. Now, an interesting property is that when you store data this way, it's the fastest way to add a large amount of values, and it's also theoretically the fastest way to pull data and modify data in a tree structure. Next, we'll look at an application from music. So if we have this, pretend this is the mouthpiece of a saxophone. Now, as Sri covered, the golden ratio is approximately 1.6. This is the bore of a saxophone. So kind of like when you blow into it, it's kind of like the big thing. Here we can see that's kind of the thing you blow into here. If we look at this, researchers found that if they design a mouthpiece using the golden ratio, the mouthpiece is, quote, it's brighter, louder, fuller, and easier to play than even the best saxophone mouthpieces that previous musicians had used before. So here we can see there are practical applications of the Fibonacci sequence even in the modern world, both in computer science and in music, which are very varying fields. So throughout this presentation, really, we've covered what the Fibonacci sequence is, how it's evolved over time, and how it continues to affect our world today.